Okay, so last time we started properties of tree. We have shown that equivalent definition of tree is every pair of vertices have a unique path, and which also means that if you remove an edge, then it creates two connected components. The tree is disconnected. So what is a disconnected tree called? It's called a forest, right? Just by your experience of English. Okay, so if you remove edges, then you get a forest. So forest is just a collection of trees. It may not be connected. And we showed that every tree has a degree 1 vertex. Any questions till now? Okay, so let us move to another property, an easy property to prove. It says that tree on n vertices has how many edges? Has n minus 1 edges. How do you prove this? How do you start? Take any vertex. Sure, but what do you do induction on? Yeah, that will be faster. So your previous property tells you that there is a, we are only talking about finite trees, so there is a degree 1 vertex, and you start from that. So let T be a tree. And V be the vertex, or be one of the vertices of degree 1. So from this vertex, what can you see in the tree? Since V has degree 1, there is an edge, and after the edge you see a subtree. Right? There is a unique subtree that this defines the whole tree. So from this picture, it is now easy to do induction. Right? So in the subtree, you have how many vertices? N minus 2, n minus 1. So here you have n minus 1 vertices. And how many edges? Induction hypothesis says that n minus 2 edges. Right, so from the subtree, attached to V, we get by induction that number of edges in T is this one edge and the edges inside the triangle, inside the subtree. So that's n minus 1. Okay, this completes the induction step. What is the base case of this induction that we have skipped? Yes, so obviously when there is one vertex, then there are 0 edges. Right, so base case is clear, and base case is trivial. So from the base case and induction step, you get the proof. Any questions? So maybe that should be written, otherwise there will be boundary issues. So base case is n equal to 1. So in the induction step, we are assuming that n is at least 2, so that the subtree will be non-empty. Okay, otherwise this n minus 2 will become minus 1 edges. We don't want that. So n is at least 2. Okay. So what is tree to do with general graphs that we will study in computer science? Can you imagine how trees will help in studying general graph that will appear in real life, which are far from trees? Trees have only n minus 1 edges, general graphs will have n square or even more edges than n square, more than n choose 2. So how do you think a tree structure will help there? Will you see trees in a graph? No, but in practice the graphs will be more complicated. So what will happen is that in general graphs you will still look at a subgraph which is a tree, and some special structures are used in computer science. One is called spanning tree. So for any graph G with vertices VE, a subgraph T is called a spanning tree. Of course, first condition is T has to be a tree. And what is the other condition? It should cover all the vertices. So the vertices of T should be everything. Okay, so it covers all the vertices. So when this happens, then this T is a rather special subgraph of your arbitrary graph. And so now in algorithms, you come up with extremely fast algorithms to compute a spanning tree. And usually what happens is you have actually weighted edges, vertices are also labeled with numbers. So generally you want a minimum spanning tree or a maximum spanning tree. Okay, so those are the optimization problems you solve. There are many famous algorithms for that. But here, see, there is no optimization question. It is just this question of finding a spanning tree. Can you design a fast algorithm? What's a constructive way to discover a spanning tree in this undirected, unweighted graph? You can just do this incrementally. You start, the graph is obviously, you are given a connected graph, otherwise there will be no spanning tree. Is that clear? If the graph is disconnected, then there cannot be a connected tree covering all the vertices. So you are given a connected graph, so you start with any vertex, and that is a tree of size 1 already, right? Then you find its edges, its neighbor, include that. So now you have a tree of size 2, and you do this incrementally. Then you will get a spanning tree. So that is rather simple. For a connected graph. So you can develop it iteratively, kind of using induction. So in the base case, you start with a vertex. So let S1 be some vertex, and in step 2, yeah, you grow S2, so you have S1 union a neighbor of V. Right, so you have this picture. You have V and you have some neighbor, let's say V2. Right, that's your S2. What next? How do you define S3 now? You just pick a neighbor to this dotted part. So there will be either a neighbor of V2 or a neighbor of V1. If none of these have neighbors, it means what? That the graph is over. Right? It means that V2 edge is actually the graph G. So as long as the graph exists outside this, you can find a V3. And then this bigger thing is your S3. Right, and so on, you keep developing this. So now let S3 be S2 union a neighbor of the set S2 as a whole. Right, S2 has two vertices, find a neighbor of any one of them. If it doesn't exist, then you stop. If it exists, then you have S3. So and so on. To get Sn. And now you prove that as an exercise that Sn is a spanning tree. And it's a very simple algorithm. It's a linear time. It's just a linear scan on the graph, on the vertex set, in fact. It's a linear, it's an algorithm with time complexity linear in the number of vertices. So order n time. Any questions? Can there be an algorithm faster than n time? There cannot be, right? Unless you see all the vertices, you cannot cover them. So this is an optimal algorithm. You cannot do faster than this. Yes, good question. So what is assumed is that you are given the graph as an adjacency list. So you will just go over a vertex and the vertex V's linked list, you will just pick the first element. Well, you implement it. You have vertices and you have linked list to each vertex, which are the neighbors of vertex V. So you, for V1, well, you have picked V1, then after that in V1 you look at, you pick the first element in the linked list of V1, that is just constant access, that call it V2. And next time you now look at whether V2 has anything. If it has something in the linked list, then you pick that. So yeah, you have to do this carefully, but it can be implemented. I'm not giving the implementation, but you can complete it. So this is as fast as it gets. In later courses, you will see finding minimum weight spanning tree, which is a much harder question because now the vertices are labeled with numbers. Vertex 1 has number 10, some other vertex has number 1000. So you have to go over these vertices and pick not vertices. Vertices you have to pick, the edges. So these weights are on the edges. The edges are weighted. So in the tree you are actually picking edges. So you have edges are a lot, they are like n square or more. So you have to collect the edges that are of smallest weight, and yet they form a spanning tree. Right? So this is a true optimization problem because this number of possibilities is enormous. You have 2 raised to n square choices. So this is impossible to do even for a graph of size 100 unless you use a very clever algorithm. Those things you will see in algorithm courses. Any questions? So then we move to a host of problems which are quite important in computer science, which is tours on a graph. It is again to do with connectivity and in particular walking in a graph, but what a tour will mean is that you want to walk in 2 different ways. One way is you try to cover all the edges without repeating any edge. Okay, that's one kind of a tour. Other tour is you want to cover all the vertices without repeating any vertex. Okay, so these are 2 different problems. So given a connected graph, is it possible to visit all vertices, respectively all edges, not at the same time? Either we are looking at the vertex problem or we are looking at the edge problem, touring all the vertices or touring all the edges, without revisiting that object. Okay, that's the family of problems called touring the graph. Sometimes this is easy and sometimes it is extremely hard. So at this stage, when you don't know any real computer science, can you guess which one is easy, which one is hard? Sorry? Yeah, so why do you say vertices is hard? Touring all the vertices is hard? Okay, but what about the vertex case? Sorry? Those 2 opposite answers. So let's see what happens. So this vertex touring the vertices problem this is called Hamiltonian cycle problem or Hamiltonian circuit. Hamiltonian cycle, Hamiltonian circuit, Hamiltonian tour, it's all the same. But we'll go with Hamiltonian circuit problem. And touring the edges is called the Eulerian circuit problem. Okay, so both are great mathematicians, but Hamiltonian is far harder. Okay, in fact, if you can find a Hamiltonian circuit in general for a given graph, If you can write a C program, then you can solve almost all the problems in computer science. Okay, almost all the practical problems in computer science reduce to Hamiltonian circuit problem. On the other hand, Eulerian algorithm we'll give today, which is very fast. Okay, there is a vast difference amongst these two. You may be confused why there is this difference. Well, we are too. So let's start with the easy one. So Eulerian circuit problem starts with a story which probably is true. So the story is through this picture, yeah, which will not be a beautiful picture. So in some sense, what this is supposed to show is there are these rivers flowing. Okay, so the dots is the water, and there are bridges given. So there is a bridge here. So bridges are in red. Okay, so how many bridges are there? There are 7 bridges, right? And which city is this? Sorry? Königsberg is the city, right? You have a good education. So this is the Königsberg bridges problem. So in this part of the city, you have this river structure, and on them you have 7 bridges, and let's draw the regions or name the regions. So regions are, this is the C region, this is A, this is B, and this is the D region. Right, so clearly the regions are inaccessible except the bridges. Right, C is separate from A, B, D and so on. But the bridges connect them, of course. So the question here is, can you walk over, so can you find a tour which will use every bridge and uniquely? So can you walk in this, can you take a tour of this region and you want to see every bridge, but you don't have enough time, so you don't want to repeat a bridge. Right? So every bridge has to be visited uniquely. So does there exist a tour of the bridges without repeating them? So what is the answer? Yeah, the answer is no. So why is it no? Okay, so now we move to graphs for this. Right, so you have the vertices should be the regions, and the edges will be the connections through the bridges that you have. So from A to C you have how many connections? 2, right? A to B you have 2. C to D 1, then A to D 1, and B to D 1. Right, so this is not technically, I mean, the way we are working, it's not a graph, it's a multi-graph. But anyways, it's clear. It's a small example, so you'll not be confused. And you want to find a tour which will cover all the edges. Right? So that is called an Eulerian circuit. Eulerian circuit is a tour of this graph G covering each edge uniquely. Okay, that's the definition. So question here is that in this Königsberg situation modeled as a graph, is there an Eulerian circuit? Because Euler is the one who solved this. So what stops this graph from having an Eulerian circuit? Sorry? Odd degree. Yeah, so that is what Euler discovered. It's probably one of the oldest results we study in this course. No, actually we'll study more, even older things when we go to number theory. But till now this is the oldest result we study in this course. So Eulerian circuit exists. A connected graph or multigraph has an Eulerian circuit if and only if each degree is even. So what is special about even degrees? Which in this graph, it's completely false, right? Every vertex has degree odd, 3 or 5. So this is a very bad example for Eulerian circuit. So actually every degree should be even to afford a Eulerian circuit. What do you do when it is even? Yeah, so this is what we saw in one proof before, the degree 1 vertex existence in a tree. Similar thing we'll do here, that if you have even degree, then you can start walking in a way that when you enter a vertex, you leave it by a different edge. So entry and exit edges, you will make them different. That's the basic principle. There is an easy case, which is if you assume Eulerian circuit existence, then you can show even degree. This again is since we don't reuse an edge in the circuit or in the tour, for a vertex, it is automatically true that the edge you have used to enter, you will use a different edge to exit. So there is a pairing of edges that happens. Entry exit edges at any vertex V get paired. Yes? Say that again. Odd degree of vertices, what do you mean? Like this? Sorry? No, vertex V is this. If you enter like using this edge, then you have to leave by a different edge. Yes. No, no, but the circuit has to come back to the vertex. No, 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 that is the definition. It's a tour. It's a tour, so you have to come back where you started. No, no, you cannot ask why. That I will set. So, tours starting and endpoints are the same. The source and destination are the same. So the U example and other examples don't apply. But anyways, this local thing that I am saying, that so there are two cases basically. Either this V is an intermediate vertex that you never saw, or you haven't seen yet as you are taking the tour. So in that case, when you are entering V, you cannot just sit there. You will be forced to move. So you will have to take a different edge, which is here the orange edge. Or the second case is that you have already seen V because you started from V. Then you can stop here. Then you have to stop here. The tour will end. In either case, the entry-exit edges, they are paired and they are different, right? So they get paired and they are different. So because of this pairing, when you look at any vertex, you will see that the degree is even. It's a multiple of 2. Is that clear? For every vertex in the graph. So the harder case is actually what happens when you are given a graph with even degree everywhere. How do you discover, let's say algorithmically or on a computer, how do you find the tour? So let G be a graph with degree of V even for every vertex. Right, so what do you do here? How to find a tour? So basically start with a vertex W. That's your source. The tour starts at that. And follow this principle. You basically go from W to a neighbor. And there will be an edge available different from the entry edge because degree is even. You take that and you continue. What happens after some steps? There are only finitely many vertices to go, right? So at some point, you will come back to this vertex. So let's draw that. So W, then you go somewhere, then you take a different edge. Then a different edge. So you basically get a cycle. Let's call it C. Okay, but what is missing in this walk? Yeah, many, I mean, either you have this, so either this is the graph, then you are done. Either we are done, or G has more edges. G has unwalked edges. Right. So in this case, then what happens is, sorry. So there will be a vertex, let's say W1 somewhere, let's say here, with an edge outgoing, which is different from the edge that we took in the cycle. Right, and which then there is this whole graph structure. It will enter the cycle again. I mean, it has to enter because of the degree even condition, right? Because here you have to come back, and it may come back. It may meet the cycle many times, but at least twice. But it may be more. We are not saying anything about that, because W1's degree has to be even. So it cannot be that the blue thing never comes back, because then the degree will be 3. So these kind of structures will be present. Now, let's say W2 is here. I can also make it general. Let's say this is WK, the kth vertex, and something hanging from this that we have not walked. Okay, so this first structure we can call H1, this we can call HK, and so on. So basically, formally, when you have to write, you will say that so let H be the subgraph, G minus the cycle, or excluding the edges of the cycle. Okay, so because these cycle edges you have already walked, so you remove them. What remains is H, and that H is has these parts, H1 to HK. So let H1, H2, HK be the connected components of H. Okay, and what are these vertices W1 to WK? These are the, let's say, the first vertex which helps you to go from cycle to H1 or HI. So let Wi be the first vertex. In the cycle that takes you to HI. Okay, so these are the formal definitions of objects in that diagram. So the strategy is simple. You walk the cycle, then remove the edges that you have walked. So if nothing remains, you are done. If something remains, then there will be connected components. It may be 1 or it may be 100. Let's say it's K. So those are H1 to Hk, and the entry point to Hi is called Wi. Okay, so that is the setting. What do you do now? Remember, your goal is to find an Eulerian circuit, and all you have done till now is find a cycle. How do you grow this cycle to an Eulerian tour? Yeah, so this red and orange edges are done. Now you focus on the blue. So from W you take the blue edge, and since H1 is a strictly smaller graph, by induction you assume that you can compute the Eulerian tour in H1. Okay, so this is a proof by induction, or in programming it's recursion. Use induction to find Eulerian tour in H1, starting from W1. Okay, so that will be the blue, say it's the blue Eulerian circuit inside the connected component or inside the graph H1. What do you do with it vis-a-vis the circuit that we have already walked? You just glue the two tours, right? From W you come to W1, you take the blue tour, and then you proceed with the red edge out of W1 as you would have done in the cycle. So you do this gluing process. So glue W1, it may be a path, W to W1 in the cycle C to this Eulerian circuit. Let's call it Euler H1. And which you glue to W1 onwards in the cycle, and go up to W2. Okay, so walk from W to W1 in a leisurely way, nothing to be done there, you just follow the cycle. Then when you hit the first block W1, you shift to the graph H1, take the tour there. Then you again start in a leisurely way to walk from W1 on the cycle, and you keep doing it till you reach W2, and at that block you again shift to H2. Okay, and this way you would have covered all the edges, and this is a Eulerian tour for the whole graph. Till Wk, and then from Wk to W1 to W, just W. So this is an Eulerian tour. Of the graph. Okay, and all we have used here is starting degree was even. Something else we used which I did not write. Why is it that you can do induction on H1? I mean, if H1 is a general graph, it may not have an Eulerian tour. So why did you accept so casually when I said that use recursion? Yeah, H1 also has degree even. That's what you have to show. You have to show that this, after removing the cycle edges from the graph, the whole graph in fact is still even degree. I mean, every degree is even. Why is that? Because every vertex, if we have removed edge, we have removed 2. Right? So even minus even is even. So this is why the remaining graph H is in fact, so that is also true here. H is even degree. And from that you can deduce that all these connected components are also even degree. And so you can do recursion. Okay, that was the key thing in fact. Otherwise you cannot recurse. Any questions? Okay, so that is Euler. You immediately get an algorithm. So implement this as a fast algorithm. Okay, this proof is itself an algorithm. And this theorem then obviously tells you that the Königsberg bridge problem, there is no Eulerian tour. So that's the end of the story. So next thing is Hamiltonian circuit. It's path or circuit. Or cycle. We'll use these things interchangeably. So circuit and cycle is the same, or tour is the same. Path will be path. That's different. That's possibly different. So what is the definition? So a path x0, x1, xk is called a Hamiltonian path if it goes through all the vertices of the graph. That's the only condition, and since it's a path, vertices here will not repeat. Hamiltonian circuit is, or Hamiltonian cycle is so if x0, x1, xk is equal to x0, goes through all vertices, then it's called a Hamiltonian cycle. Okay, so it's basically a cycle through all the vertices and no vertex repeated except the source and the destination. In a cycle or in a tour we always have that. And finally, a graph that has a Hamiltonian cycle is called Hamiltonian. Okay, so these are very special graphs. Graph G with a Hamiltonian cycle is called a Hamiltonian graph. Okay. So can you give an example of a Hamiltonian graph? Examples are numerous, right? You can just look at a cycle. So Cn this is Hamiltonian, just the cycle itself is a Hamiltonian cycle. Or you can look at the complete graph. Right, complete graph in particular has a cycle Cn. So you can just walk that, that's a Hamiltonian cycle. What about a complete bipartite graph with m plus n vertices? Is it Hamiltonian? Why not? Sorry, not directed, undirected. Vertices u to v. So obviously all the cross edges are there. When do you think there is a Hamiltonian cycle and when not? Sorry? No, that will not do. So m plus n is even, right? So what can happen is 1, 2, 3, 4 and 1, 2. And you have all these connections. Unfortunately, you will not have a Hamiltonian cycle here. Going from 1 to 1. So what you will need is m and n to be equal. That's the only case. Hamiltonian if and only if m equal to n. Prove this as an exercise. Yes. Sorry, if m is? Well, that's a bold claim. So you have 1, 2 and you have 1. Sorry? So that doesn't work. If you have 1, 2 and 1, 2, then you have, right? Then you go from 1 to 1, then 2, then 2, then 1. I should also rule out both equal to 1. That is also not possible. So this is greater than 1. So m equal to n and at least 2, then you can see that there is a simple Hamiltonian cycle. Otherwise, you have to show that it doesn't exist. Simple properties of a Hamiltonian. What happens if you add edges in a Hamiltonian graph? Does it remain Hamiltonian or not? Right, so if you have a Hamiltonian cycle already, then adding graph cannot hurt. So Hamiltonian G remains so. If we add edges. So addition of edges is not a problem. Second property is it has two disjoint paths u to v for every uv. So basically it's a bi-connected graph. Why is that? It's not only connected, but it is bi-connected for any pair of vertices. There are two different paths. This is again clear from the cycle itself, right? And the strong thing is that since the cycle covers all the vertices, so you get a property for every pair. So the question is, given a graph, can you test whether it is Hamiltonian? And if you can test, then you can whether you can find a Hamiltonian cycle, or can you find between source and destination a Hamiltonian path, right? So these are the computer science computational questions. What do you think is the answer? Well, I already said that if you solve this, then you solve all the problems. So then the answer is no, conjecturally. We don't have a proof for this. So what you will see in future courses is that finding a Hamiltonian path, okay, this problem of Hamiltonian path finding, this is NP complete. Which cannot be explained here, but for you laymen and women, just think of it as very hard. Okay, we will not define this, but this is just saying that this is a very hard problem, and not only it is very hard, this completeness basically means that all other interesting practical problems reduce to it. So if you solve this, then everything else gets solved. These are problems of all types: combinatorial, number theoretic, algebraic, optimization, scheduling, and whatnot. Okay, so this simple two-state graph problem has infinite complexity inside. So needless to say, we don't know of good necessary and sufficient conditions, by which I mean, like in this theorem for Eulerian circuit, there is a if and only if statement, right? Like if this happens, then there is always an Eulerian 2, or otherwise it is not. That kind of a theorem doesn't exist for Hamiltonian. So not much is known. Mathematically about this property. So we don't have structure theorems. Necessary and sufficient for Hamiltonian graphs. So necessary means that a property which Hamiltonian graphs will satisfy. Sufficient means that if a graph satisfies the property, then it should be Hamiltonian. So this one property we don't know. I mean, of course, you know the definition, but other than the definition, there is no interesting structural property to talk about. Nevertheless, there is a theorem that we will prove next time. That's Dirac's theorem. From 1952, that a simple graph on n vertices is Hamiltonian if every vertex has large degree. Greater than or equal to n by 2. Okay, if you have a graph that has essentially a lot of edges, everywhere you see there are many edges, and quantitatively every vertex has degree at least n by 2. So if n is odd, then it means n plus 1 by 2, at least n plus 1 by 2. Then the graph is Hamiltonian. Okay, but this is not a, I mean, it's a sufficient condition, but it's not a necessary condition. So this still misses a lot of graphs, especially graphs where edges are few, degrees less. So we'll prove this theorem next time. There are many generalizations of this theorem, but we'll just stop at this.